Okay, so today I want to talk to you about the photoelectric effect, which in the curriculum falls under matter and materials and is called optical phenomena and the properties of light. And under the photoelectric effect, we have the photoelectric effect and emission and absorption spectra. So I have here a picture of the electromagnetic spectrum, which you start learning about in grade 10, with all of the different kinds of waves and their properties. Here is a little curve showing you their frequency and wavelength, and you can see that the visible light that we see is here in the spectrum here when you go from radio waves to gamma rays. So this is a long wavelength, this is a short wavelength. And over here in the corner I have a little animation of how exactly electromagnetic waves are propagated. And you know that if you have a moving charge, it creates a magnetic field, and if you have a magnetic field, you can create a current. So that is how electromagnetic radiation is propagated. It's an accelerated charge which makes a little electrical field, which makes a magnet. They're at right angles to each other, and then they propagate themselves. And so one of the properties of electromagnetic radiation that you should remember from grade 10 is that it can travel through a vacuum. So we are going to be talking about this electromagnetic radiation in this topic. So you have mostly learned about the wave properties of light so far, but light has got a both wave and a particle property. And this photoelectric effect is all about the particle properties. The wave properties are things like reflection, refraction, diffraction. So for instance, if you put white light through a prism, you can split it into the spectrum or the colors of the rainbow. This happens via refraction. If you pass a nice straight wave through a slit, you'll see the wave will spread out. Okay, this is diffraction. And then as well, if you bring a wave and you go from one medium to another medium, you can bend it, which is what's going on over here. But we learn about this in grade 11 with that dude with the weird names, Principal Huygen, I don't know how to say his name. So these are all wave properties that we've looked at. But light also has a particle property. You can shine a light and cause a flow of electrons, or a flow of electrons is an electric current. So this was discovered if you have an electroscope, like a gold leaf electroscope here, and the electroscope is charged, the leaves are apart, okay, and you shine, for instance, light that is red, and it's only red light, it's not white light with all the colors, it is monochromatic or only red light on it. If it is positively or negatively charged and you shine a red light on it, absolutely nothing happens. If you shine an ultraviolet light on an electroscope and the electroscope is positively charged, absolutely nothing happens. But if you shine an ultraviolet light on it and it's negatively charged, you will see that as soon as you shine the ultraviolet light on it, the leaves start to come together. And how does this happen? The leaves, if it was negatively charged, the leaves had the same charge. There were an excess of electrons. They were repelling each other because like charges repel. So the only way for the leaves to come back together is if electrons are lost. So this ultraviolet light, simply by shining on this conductor here, metallic conductor, can cause electrons to leave the surface of the metal. So this is proof that light is a particle. Now, in this topic, you can cut through all the waffle and you can answer most of the questions if you write this down. If you shine light, that's a frequency that's less than the frequency. Remember, we had the different color lights over here, red and ultraviolet. So the frequency is related to the color of the light. If you shine light of the wrong frequency and it's too low, no electrons come off. If you shine light of the correct frequency, you can cause electrons to jump off metal. So check here, red light, no electrons. Green light, some electrons bumping off. And blue light, electrons bumping off at speed. Okay, so if your frequency is high enough, you will get speedy electrons coming off. If it's too low, no electrons. And if you have a bright light is a high intensity light, you will push off the most photoelectrons. So this is the most important thing, and you can write this down and answer most of the questions based on this information. So I've put it right at the front, so if you're bored of listening, write this down, leave the video, go and attempt the questions. Okay, so let's think about this a little bit more and a little bit about the theory behind it. In the electromagnetic spectrum, there are lots of waves. The waves are all different frequencies, okay? And this frequency is related to the energy of the wave and other properties of the wave. But the electromagnetic spectrum, it actually behaves like the energy is not continuous, but actually in fixed little packets of energy. These little packets are a certain size, and it's called a quanta or a quantum of energy. The energy packets are just a fixed size. You can't get like half a quantum or a quarter of a quantum. It's a fixed size. So if you look in your guidelines, it'll tell you a photon is a precise amount of energy, a quantum associated with electromagnetic radiation. And this is important because we are going to swap photons for electrons. So how does this work? It works because of our understanding of it is related to the Bohr model of the atom. So in grade 10, you learnt about Bohr and Rutherford and Dalton and all of those theories that came about what the atom looks like. And Mr. Bohr was the one that said, if you have an atom here, can you see my atom? Here's the nucleus, and here are all of the electron shells with electrons orbiting the nucleus. So Mr. Bohr said the electrons occur at different energy levels. So with the photoelectric effect, here's a photon of light. It's coming in here, a little electromagnetic ray. If it hits an electron and it's got in the right amount of energy, the photon comes, hits the electron absorbs the energy, the photon disappears, it ceases to exist, but the electron gets energy to jump up to a different energy level in the atom. Okay, so it comes in, photon in, whacks the electron, the photon disappears, but we've now got a speedy electron jumping to another energy level. Okay, if the energy of the incoming quantum of the photon, the packet of energy in the photon, is not the same size as these energy levels in the Bohr shells, the atom just gives off the energy, it just bounces off again, it's reflected, and the metal looks shiny. But if the photon matches the energy level of those little electrons in the atom and the different distances of the shells, the electron gets excited and it jumps up to a higher energy level, and it's our little excited electron. But electrons don't like to necessarily be so excited. So what they do is they fall back down to the lower energy level that they came from. And so then when they fall back down, they release a certain size amount of energy that is equivalent to the difference in energy between the energy levels. Okay, so this energy can come off here as either light or heat. So in comes the light, it grabs an electron, the electron swaps the energy and it goes into a little bit of kinetic energy, goes up to a high level, it's not happy in that excited state and it drops back down, and then it emits energy again as either light or heat. So this is where the definition comes from. This is your guidelines definition. The photoelectric effect is the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that surface. So if you make this in simpler English, if the light's the right color, which is related to the frequency, which is also related to the energy, it's more the frequency of the light, the energy of the light than the color, but it helps us to think of it with the rainbow and the color. So it's actually more the energy, okay? And if it shines, is incident on the metal surface, boom, an electron can pop off if the light has got enough energy. Okay, So here's a little picture of it. Here's a metal surface, and here are all these little electrons sitting in the metal surface. In comes my light, but check, this light is yellow light, and these photons of energy are too low. They're below the threshold energy needed, and the electrons are like, meh, not enough energy for me. And they just sit there, and the metal looks a bit shiny because the light bounces off. Okay. But if you shine like ultraviolet light, can you see this one is a nice purple color? If you shine it on that same metal, as the photon comes in, it gets absorbed by the electron, and the electron goes whee off the metal with an escape velocity or a maximum kinetic energy, because velocity and energy are closely linked, and the mass of an electron is fixed. So that's what happens if the light is the right color. The photons of light are picked up by the electrons, and the electrons are emitted from the surface of the metal. How can this happen? It happens because in a metal, remember when you learn about metallic bonding, you have the positive cores, okay, and then the very outermost shell overlaps, and you've got this pool of delocalized electrons in what's called the conduction band, okay, and it's these valence electrons that are emitted, and when they're emitted, they become a photoelectron. So we often talk about zinc in the questions, and there's examples easy to see on the internet, because zinc is common and UV light is common. So if you put UV light on zinc, you will pop little electrons off. Okay, but if you've got another metal, you'll have a different amount of energy, because it all depends on where the pool of delocalized electrons is, how far is it from the nucleus of the atom, like that. So when we do things, obviously this is physics, we need to be able to do calculations. So we use this formula, E equals HF, okay, and this E is the energy of the incoming photons in the light. It is equal to Planck's constant, which you will find on your data sheet, times by the frequency of the light. So the short story on this is the energy is the energy is proportional to the frequency. Okay, so if you have a high frequency light, you have a high energy light. If you have a low frequency light, you have a low energy light. You also need to remember with this though, that we use the wave equation. Okay, we don't always get given the information in terms of frequency. Sometimes we get given the information in terms of lambda, the wavelength. So this is the wave equation, that the velocity is equal to the frequency times the wavelength, okay? But we are dealing with our friend Mr. Einstein and what he discovered about electromagnetic radiation. Mr. Einstein checked the speed of electromagnetic radiation, and it is a constant for all electromagnetic radiation, and this constant is called c, the speed of light in a vacuum, which you'll also find on your data sheet. And this is equal to the frequency of the light times the wavelength of the light. So because C is a constant, this means that the frequency will be inversely proportional to the wavelength. Okay, so if you have a high frequency, look over here, this is a high frequency light on this side, and if you measure between 2 points in phase, which is a wavelength, you will get a short wavelength over here. But if you look over here, this is a low frequency. On this side, the wavelength is long, okay? So a low frequency will give you a long wavelength, which means a low frequency and a long wavelength has not got a lot of energy. So here you can see in a little bit of an expanded spectrum, if you take the energy is equal to Planck's constant times the frequency, you using C equals F lambda, you will end up with the energy is equal to Planck's constant times the speed of light in a vacuum over lambda. Okay, so high frequency light is high energy light, short wavelength light is high energy light. Look in the little picture here. Here is the frequency 10 to the 20. Here is the wavelength 10 to the minus 12. So this is a small number. This is a big number. But this here is where you've got high energy waves. This here is low energy waves. Low frequency, low energy, but a very, very long wavelength. Okay, let's stop there for now.